What she found was a signal so weak it had been sitting there, essentially unnoticed, hiding beneath years of noise. A thin, almost continuous hum, distinct from the loud, occasional whistle events triggered by solar shock waves that scientists already knew about. Unlike those rare, dramatic bursts, this new signal was persistent. A steady drone rather than an occasional shout, and it too tracked the density of the space Voyager 1 was moving through. Researchers began calling it a plasma wave emission. The implications were enormous. For the first time, scientists had something closer to a continuous, real-time readout of what interstellar space is actually made of, instead of relying on rare, lucky solar events to get a single snapshot every year or so. Think about what that means. Humanity now has a machine built in the 1970s with less computing power than a modern calculator, sitting nearly 16 billion miles from home, quietly recording the ambient hum of the galaxy itself. Data that reveals how dense the space between stars really is, how it fluctuates, how it moves. That persistent hum reveals density fluctuations on a scale of roughly an astronomical unit, tracing turbulence in the interstellar medium that no telescope on Earth could ever directly measure. This is not a metaphor for discovery. This is discovery happening in near real time from a machine that was never designed to still be functioning at all. But nobody, not even the scientists who found it, fully understands why the hum exists in the form it does. The possible explanations on the table include thermally excited plasma oscillations and something called quasi-thermal noise, but researchers openly admit these remain educated guesses, rather than confirmed answers. That is the part that should sit uneasily with you. A machine humanity built before some of your parents were born is recording a signal from the space between stars, and the honest answer from the scientists studying it is, we are still not completely sure what's producing it. What most people are not seeing in the headlines is that this uncertainty is not a failure. It is the frontier. It is what real exploration actually looks like. Not a clean answer, but a persistent, faint, unresolved question drifting back to Earth one transmission at a time. And this is where everything changes, because right now, in real time, engineers are racing against Voyager 1's dying power supply to make sure that hum keeps reaching us for as long as physically possible. The plan has an almost theatrical nickname inside JPL, the Big Bang. It's an upgrade designed to squeeze more operational life out of the spacecraft, potentially even allowing some of the instruments already shut down to be switched back on in the future. But nobody is reckless enough to test something this risky on the more historically significant, more fragile Voyager 1 first. The team is testing it on Voyager 2 first, since it has slightly more power in reserve and sits closer to Earth, making it the lower risk candidate, with tests scheduled for May and June of 2026. Only if that test succeeds will engineers even attempt the same fix on Voyager 1, and even then, not before July. This is not a guaranteed victory. This is a calculated gamble on a machine that cannot be repaired if the gamble fails. And the stakes of that gamble are not abstract. Every watt saved is more months of listening. Every extra month is more density data from a region of space humanity may not directly sample again for decades, possibly longer. Consider the physical toll this spacecraft has already survived just to get here. One small motor inside the now shut down LECP instrument, a stepper motor that spun its sensor to scan in every direction, had operated flawlessly for nearly 49 years, and more than 5 million individual steps, and it kept working even after engineers cut its heater to save power, letting its onboard temperature plunge to a brutal negative 62 degrees Celsius. The instrument's own principal investigator, a physicist who had studied its data for decades, could not hide his disbelief, calling that kind of endurance the stuff dreams are made of. That is not corporate messaging. That is a scientist watching hardware from the disco era outperform every reasonable expectation, nearly a light day from home. Here's the part almost nobody talks about, and it should terrify anyone who understands how fragile this entire operation actually is. Voyager 1 and Voyager 2 can only be commanded through one single antenna complex on the entire planet capable of reaching them. Deep Space Station 43, located in Canberra, Australia. That antenna went offline for major upgrades between May 2025 and February 2026, with only a handful of limited operational windows available in August and December of 2025. For most of nearly a year, humanity's ability to speak to its most distant machine, or hear anything back from it, hinged on a single piece of ground infrastructure undergoing maintenance. No backup, no alternative. If something had gone wrong on the spacecraft during that gap, there may have been nothing anyone on Earth could have done in time. Think about how precarious that actually is. A machine surviving interstellar radiation, cosmic ray bombardment, and temperatures that would shatter most modern electronics. Its entire lifeline back to civilization running through one dish in one country that was, for months, simply switched off for repairs. So where does this actually leave us? By most current estimates from mission engineers at JPL, Voyager 1 is expected to keep functioning into the early 2030s before its power supply finally drops below the threshold needed to run even its remaining instruments. Some estimates stretch slightly further, suggesting the spacecraft could keep transmitting basic engineering data for a few more years beyond that. But eventually, and there is no version of this story where it does not happen, the last watt runs out. The plasma wave instrument goes silent. The hum stops arriving. Not because the interstellar medium stops vibrating, but because there will be nothing left on board with the power to listen and nothing left with the power to tell us about it. And here is the detail that should stay with you long after this ends. When that final shutdown happens, Voyager 1 does not stop. It does not fall. It does not slow down. There's no friction in interstellar space, nothing to drag against it, nothing to pull it back. It simply keeps moving forever, carrying with it the golden record. A gold-plated copper disc assembled under Carl Sagan, engraved with greetings in 55 languages, alongside music, images, and a map showing the location of Earth relative to nearby pulsars. A silent, powerless artifact drifting through the galaxy on the off chance that someone or something someday finds it. No power. No transmitter. No way for us to ever know if it worked. Just a physical object launched by a species that no longer exists in the same form it did when the launch happened, continuing on a trajectory that outlives everyone who built it. So think about what is actually happening right now, in this exact moment while you are reading this. Nearly 16 billion miles away, a machine built with 1970s technology running on a power source that has been quietly dying for 49 years, having already sacrificed most of its own senses just to survive, is still recording a faint, unexplained hum drifting through the space between stars. A hum scientists still cannot fully explain, coming from a region of the galaxy no other human-built object has ever reached. In a matter of months, that same machine will cross a distance so vast that a single hello sent from Earth will take a full 24 hours just to reach it, and another 24 hours for any answer to come back. And somewhere in the next decade, the power will finally run out. The listening will stop. And Voyager 1 will keep moving anyway, forever, carrying a message from a civilization that may not even remember exactly what it sounds like. What happens when the last signal finally goes quiet? What that hum actually is, and whether it will ever be fully explained before the instrument recording, it dies for good. Whether the Big Bang Fix buys Voyager 1 the extra months it desperately needs, or whether this is the beginning of the final countdown nobody wants to admit has already started. Nobody currently has those answers. Not the engineers at JPL, not the physicists studying the plasma data, not anyone. All we know for certain right now is that something is still out there, still listening, still sending back a sound humanity has never fully understood, and the clock on how much longer we get to listen with it is already running out. Somewhere past the orbit of everything you have ever seen with your own eyes, a machine older than the internet, older than cable news, older than almost every person reading this sentence, is still awake. It launched before smartphones, before the Cold War ended, before most of the world had ever touched a computer. It has outlived its own engineers. It has outlived its own mission plan. And right now, in the coldest, emptiest region humans have ever measured, it is still listening. Not metaphorically, actually listening. And what it is hearing is something almost nobody has bothered to explain properly. Its name is Voyager 1, and to understand why what is happening to it right now matters, you have to first understand how far gone it already is. This is not a satellite orbiting Earth. This is not a probe circling Mars. Voyager 1 left the solar system entirely, crossing the heliopause, the outer edge of the sun's magnetic influence, back in August 2012. Everything beyond that boundary is interstellar space, the space between stars, the kind of environment no human-built object had ever touched before, and only one other object, its twin Voyager 2, has touched since. Think about what that actually means. Every planet, every asteroid belt, every comet you have ever heard of, all of it sits inside a bubble the sun blows around itself. Voyager 1 popped that bubble and kept going. Right now, in the middle of 2026, Voyager 1 sits roughly 40 billion kilometers, or about 15, 8 billion miles from Earth. Read that again, 15.8 billion miles. Numbers like that stop meaning anything to the human brain. So here's the part that actually lands. NASA has now calculated the exact moment Voyager 1 will become the first human-made object to reach one full light day from Earth. The distance light itself takes 24 hours to travel. And that moment is locked in for November 18th, 2026. Once that threshold is crossed, something strange happens to the very idea of communication. Mission engineers are not exaggerating when they describe it as a delay measured in calendar days rather than minutes. Right now, a command sent from Earth already takes about 23 hours to reach the spacecraft. By November, that becomes a full 24. Send a signal Monday morning, and you're not getting anything back until Wednesday. That is the reality of talking to something this far away. And here is where it gets worse. Voyager 1 is not just far, it is dying. Slowly, deliberately, and by design, because the alternative was dying faster. The spacecraft runs on plutonium, 3 radioisotope thermoelectric generators that convert the heat of radioactive decay into electricity. There is no sunlight out there strong enough to power solar panels, no refueling, no backup shipment arriving. What launched with it in 1977 is all it will ever have. And that power source has been quietly bleeding out since the day it left the launch pad. The generators produced roughly 470 watts at launch. They now produce somewhere around 250 watts, and they lose about 4 watts every single year, with no way to reverse it. That is not a technical footnote. That is a countdown clock that has been running for 49 years, and it does not stop. So what do you do when your machine is dying nearly 16 billion miles from the nearest repair shop? You start making sacrifices. One by one, instruments that once made Voyager 1, one of the most capable scientific spacecraft ever built, have been switched off. Not because they failed, but because keeping them on would kill the whole mission faster. This wasn't a panicked decision made in a crisis. According to mission records, the order in which instruments would be shut down was mapped out by engineers years in advance. A slow, deliberate triage plan for a machine they knew would eventually run out of everything. And this is where the story stops being abstract and starts becoming urgent. On February 27th, 2026, during a routine and fully planned maneuver, something happened that was not supposed to happen. Voyager 1's power levels dropped unexpectedly. Not catastrophically, not fatally, but enough that engineers at NASA's Jet Propulsion Laboratory understood immediately what was at stake. If the power dropped any further, the spacecraft's own onboard safety system, its undervoltage fault protection, would kick in automatically and begin shutting down components on its own without human input, without human judgment, in a location so remote that fixing a mistake could take weeks. The team had one option: act before the machine acted for them. This is not chaos. This is discipline under pressure, executed from a control room on Earth, aimed at a machine that cannot be touched, cannot be seen, and cannot be recovered if something goes catastrophically wrong. So on April 17th, 2026, NASA sent the command. Engineers powered down the low-energy charged particles experiment, an instrument that had been running almost without interruption since 1977. Nearly 49 consecutive years of continuous operation, an almost unbelievable engineering record, gone dark with a single transmitted command. This was not some minor gauge. The LECP tracked ions, electrons, and cosmic rays streaming in from both our own solar system and the wider galaxy, and it had delivered critical data about the structure of interstellar space itself, detecting pressure waves and shifting particle densities in a region no other spacecraft has ever entered. And here is the detail that should genuinely unsettle you. Because Voyager 1 is so far away, the shutdown command took roughly 23 hours just to arrive, and the shutdown process itself took a further 3 hours and 15 minutes to complete. Somewhere out past the edge of the solar system, a computer program silently executed its own extinction. In near total isolation, hours after the humans who triggered it had already moved on to their next task. The mission manager overseeing this decision, Kareem Badruddin, put it in blunt terms that cut through any illusion of glamour. Shutting down a working science instrument is nobody's preference. It was simply the best option available. But here's the twist that most casual coverage completely misses. This wasn't the first time. The exact same instrument had already been switched off on Voyager 1's twin, Voyager 2, back in March 2025. A quiet rehearsal for a decision the team knew was coming for its sibling. Of the 10 identical instrument sets each spacecraft originally carried, the majority have now gone silent, deactivated in a carefully choreographed sequence designed by people who understood, decades in advance, exactly how this story would eventually unfold. And yet, after all of that stripping away, after nearly half a century of decay, after a power scare that forced an emergency shutdown, Voyager 1 is still doing something almost nobody expected it to still be doing. It is still listening. As of today, only 2 instruments remain operational on the entire spacecraft: a magnetometer and something called the plasma wave subsystem. And it is that second instrument, the plasma wave detector, where this story stops being about survival and starts becoming something else entirely. Here is what most people watching space content online do not fully understand about that instrument and why it matters so much right now. The plasma wave subsystem does not detect sound in the way your ears understand sound. Space is a vacuum. Nothing should travel there the way a voice travels through air. But interstellar space is not perfectly empty. It is filled with an incredibly thin, ionized gas called plasma. And when that plasma is disturbed, its electrons oscillate at frequencies that happen to fall, almost poetically, within the range of human hearing. Because those oscillations occur at frequencies between a few hundred and a few thousand hertz, scientists can run the raw data through a loudspeaker and, for the first time in human history, Actually listen to the vibration of matter drifting between the stars. This is where the real story lives. Rewind to November 2012, 3 months after Voyager 1 broke through into interstellar space. The plasma wave instrument picked up the very first tones ever recorded from beyond the heliosphere. Inside the bubble of the sun's influence, the tones had always registered low, dull, around 300 hertz. But out there, in true interstellar space, the pitch changed. 6 months later, in 2013, another tone appeared. Louder, sharper, higher pitched than anything recorded before, and it told scientists something unsettling. The interstellar medium around the spacecraft appeared to be getting denser, and it was happening fast. Gas that was supposed to be sparse and empty was thickening, and here is where it gets worse, because that was over a decade ago, and the story did not stop there. In 2021, a Cornell University doctoral student named Stella Ocker went digging back through years of Voyager 1's raw plasma wave data, hunting for something faint, something buried beneath the obvious signals everyone else had already studied.